Started. Good afternoon and welcome to the session. My name is Ming Xu. You can call it Ming Zhu, it's fine. And I've been in the HPC space for about 22 years, so quite a long time. And so how many of you have done multi-core programming before? Just a show of hands. Okay. Anyone have done an application that scale out to more than one box? A show of hands. Quite a few people. Okay. And well, one benefit you get having someone with 20 years of experience talking on this subject is that you're going to hear something really fresh, but in fact it's 20 years old. And some of the things may appear really old and outdated. Actually, it still applies today. All right, without further ado, let's get into a video. So in this video, here's a scenario. A customer calls up a bank and says, I want to buy a few Asian options, right? So, and the trader in bank A will fire up a spreadsheet, and it's going to take 3 minutes to complete. While he has the customer on the phone, is trying to keep him interested and engaged. He's going to keep asking how his spouse is doing, about the pets, about children. Whereas the other trader using HPC server and is doing a scale-out application, as you can see that, well, the spreadsheets, well, this value is popping up really quickly. And in a matter of 7 seconds, it's got the price. So, needless to say, that if Bank A is not doing what Bank B does, then sooner or later, Bank B is going to get most of the business. So, this session is about what happens in that 7 seconds. First of all, we're going to talk about the application patterns and the solutions. Because I haven't seen any one-size-fit-all kind of solution for a whole spectrum of HPC applications. And then we're going to introduce the HPC SOA programming model, and which is really good for this type of problem that I just showed you. Then, at the end of the session, hopefully you'll be able to see for yourself that HPC server does deliver on time to solution. And at the end of the session, I certainly hope to deliver you guys with a set of helpful tips so that you can go ahead and model your applications and fine-tune your application performances. Let's go back to that spreadsheet. I didn't write that one. I basically took off of this classical financial modeling book by Simon Benninger. And so the bulk of the calculation comes from these 10 by 10 ranges, Excel ranges. And the actual flow goes like the following. As you notice, it has a nested loop, and it's sort of trying to fill the cells in a column major order. And the most inner loop, it calls price Asian option. And then populate the value in the cell, and then it's going to go ahead and calculate the average value and standard deviation of the 100 calculations. And as you note that there is really no interloop dependency. And what I mean by that? What I mean is, even though there is like 100 different iterations, but each individual different iteration can be executing any independent order. It is not required that the first iteration be executed before the second. So that's what I mean by no interop dependency. Now look at the price Asian options. It contains 1 million times 20 floating point calculations. So what is that? So an Asian option pricing basically is a stochastic process. An Asian option, the payoff is determined by the average price of a stock over a period of time. So there's no way to predict the future, and therefore, what we're going to do is to actually generate a random path. from the initial value. And so there's ups and downs with these curves. So what determines that it goes up and goes down is, in fact, determined by this random variable. So if the random variable is greater than a known p, which is the probability of the stock going down, if it's greater than that, and then it goes up. So this happens in this step. And if it's less or equal to the probability of going down, and then it will go down. So as we generate these curves, we also calculate the payoff. The payoff is set to the initial value of the stock. And then if it goes up, we have the value time the actual up jump. The S stands for the previous value, the stop of the previous steps. And the up and down is actually calculated by the mean and volatility of the stock. So that's also a known value. And we generate lots and lots of these curves. After you generate 1 million curves, you cannot see individual ones anymore. What you're seeing is the distribution, where the darker area represents where the stock is most likely going to end up. And with those 1 million calculation, you calculate the average payoff. Then you just discount that by the risk neutral rate. And that is the price of the Asian option. Okay. How many of you have confidence in the stock market now? All right. Just map that to code, because you're going to see this code pretty quickly. And I can't promise to have this big of font when I bring up the Visual Studio. So this is your first chance to look at the code. Basically, it generates 1 million, 1 million paths, and each path has 20 steps or periods. And for each step, I generate a random number. And if it's going greater than the probability of going down, basically, I have a up value. And otherwise, it gets timed a down value. Then this step just summarizes all the steps up. So at the end of each curve, I would just do an average price for that curve. And then if the average is actually greater than the exercise price of the option, and it has a positive payoff, otherwise it's 0. So this is a call option. It's a long position. So I keep adding up these paths up 1 million times. At the end of the day, I have to divide it by number of runs. There's a typo here. Number of runs equals 1 million. So that will give you 1 million, the average payoff of 1 million paths. Then I'm going to discount that with the interest rate over the number of periods. That will give me the price. All right. So let me show you a demo of this running serially. All right. So what you're seeing here is the sequential one is two iterations, two nested loops. And the outermost one iterates from column D to column M. And in the iteration, loop goes from 2 to 11, so 10 by 10. And it's going to scan through D2 to M11. That's a range of 100 cells. And you're going to call price Asian option, and then you're going to do min and max standard deviation calculation. Fairly straightforward. So I'm just going to start without debugging, run it in a sequential mode. So it's in the process of building it, launching Excel. OK. So 1 million, not running on the cluster. Now run it. So as you can see, the value keeps popping up. And it takes about 180 seconds or so. Surely we're not going to stand here and watch the kettle to boil. Let's get on to with our presentation. So we know that's slow and we need to accelerate it. And of course, you're attending the session, I'm going to tell you HPC server is the answer. But what is HPC server? HPC server comes with 2 CDs. The first CD is the OS. The second CD is the HPC computing middleware. The first CD is the 64-bit, bit-by-bit compatible Windows Server OS. But it comes with a much discounted price. I'm not a salesperson, so I'm not allowed to announce the price here. Second CD is called HPC Pack. So it contains the middleware that help you build HPC applications, help admins manage, deploy, monitor, troubleshooting your cluster, and help users running applications on the cluster. So overall, it makes the cluster operation as easy as a single box and makes developing applications on the cluster easier too. All right, so let's shift gear and talking about parallel programming methodology here. So since some of you have already done scale out to multi-core computing, I hope this concept is not really strange or foreign to you. And this is a type of concept that's been in place for over 20 years. Well, maybe longer, but it was before my time. So if I can find two things that categorize an HPC application, it has to be the relationship among the processing elements, and second one is the program structure. So as far as relationship among the processing elements is concerned, first of all HPC applications use the divide and conquer in parallel approach. So it's going to divide up the work and assign the work to a multiple processing elements. So 4 of these processing elements shows here in green boxes. The tightly coupled paradigm basically requires that each processing element at each time step does its own computation, computes its own local state, and then exchange boundary conditions before moving on to the second step. Have you ever seen one of those funny races where you have 4 or 5 people standing up and you have one person's right leg tied to the other person's left leg and they go forward? How many of you have seen that? Lots of you have seen that. That's exactly the same case here. So if you see one guy fell and then the whole team halts, that's what happened with this kind of model. Is one of the processing elements stops or crashes, the whole computation has to restart. And therefore, to ensure progress, they periodically checkpoint their states into a local disk or somewhere in the central file share to ensure that when the next time they recover, they can start from where they previously left off. Whereas the loosely coupled is a different situation. The loosely coupled basically says, I can go ahead as fast as I can. And without synchronizing among the processing elements. If I finish with one work unit, I can grab another one. With programming structure, we have the compute-driven, the loop parallel, and the data parallel approach. The loop parallel, basically, you will see loops or multiple nested loops in the application. With data parallel, basically, data parallel use declarative syntax to model the type of the data processing problems. So in this particular one, how many of you are familiar with LINQ? Okay, many of you. So this is a LINQ syntax. Basically, what it does is trying to find out among a set of babies collection, and it's trying to match up the name with the query name, with the query states, and see whether the baby's year of birth is actually within a specified range. And then when I get those set of babies, I want to sort them based on the year of birth. And so that's the data parallel semantics. With that established, now we can look at how we actually pour these applications into these quadrants. So on the horizontal axis, I have relationship among processing elements. And on the vertical, I have program structure. So all the traditional HPC applications, the ones that's most famous, the one that actually help push the frontiers of human discovery, the one that help enterprises design better products, products that require safety of the vehicle, safety of the bridges we build, product and help us predict the model more accurately, and help the oil and gas companies find where to drill the hole effectively. These are the type of application that's tightly coupled because using the car crash as an example, you divide up the whole car surface into multiple processing elements at each time steps, and it will simulate the local state. And it has to exchange boundary conditions with the other one and before we move in onto the next step. So that's the traditional one. And the type of solutions we have are OpenMP for multi-core and MPI, which stands for Message Passing Interface for scale-out solutions. We're not going to cover this today. HPC server product these kind of tools. So let's move on to the other quadrant, which is sort of the new map and reduce type of problem for searching and for data mining. We have P-Link, if you are to do it on a multi-core machine, or Dryad Link, if you want to scale out to multiple nodes. At 4 o'clock today, John Vert from my team will be giving a Dryad Link session. So if you have type of applications like that and would like to accelerate that applications and scale them out, do attend that session. Highly recommend it. Now, the type of application that I've shown you here, a lot of that comes from finance world. For example, value at risk, real-time risk, and derivative product pricing, which is the spreadsheet application that I showed you earlier. Actuarial processing in the insurance space, or generic application like Excel, UDF, user-defined function calculation. In the life science world, gene sequencing, genetic algorithms, and digital content creation, rendering. These type of applications is loop parallel, and it has lots of loops in it. But the actual loop body can be executed independent of one another. So, and the tools for that, the solution for that are many. If you want to accelerate that on a single box, TPL. In fact, we have task parallel sessions as one of the parallel computing track here. And I have a slide that shows you where they are. And if you're interested, if your application is written up in an self-contained executable, and if just by passing different parameters to the executable or different files, it can sweep a whole iteration space. And then you might consider using parametric sweep jobs that's provided by the HPC job scheduler. However, this session is focused on the SOA, HPC service-oriented platform, which helps you. The developer can simply just encapsulate the calculation in a DLL, throw the DLL to the HPC cluster servers, and then invoke calculation requests on these set of blocks in parallel. So the end result is it's fairly straightforward to accelerate applications like that. So coming back to the Excel application, from Visual Studio Tools for Office, from this object, which I showed you earlier, I can put in a set of parallel invocation statements, and that will help me, Excel, offload the calculation onto the server, so where the actual Asian pricing option is running. And doing it in parallel, the processing is overlapped, the whole cycle is compressed by orders of magnitude. Okay, frequently asked questions. Which distributed computing framework should we use here? Should we build our own? How to host the calculation logic on the compute nodes? How do I invoke calculation remotely? How do I debug my services? Printf, that's a leading question. No. Remote invocation occurs a high overhead. Do you have any performance tips? Finally, most recent question is, when I move to the cloud, do I have to learn a new API? What happens to my existing applications? How many of you have cloud on your mind? Very clouded mind. All right, okay. So I'm sure you have other questions. Let's start with these for the rest of the session. First question is actually a pretty simple one. It did not take us a lot of time to make the decision. We basically decided that we're going to use WCF, Windows Communication Framework. How many of you have used WCF before? Okay. So first of all, it's the established service orientation platform and comes with a set of tools. So with service orientation, it's really easy for our developer to encapsulate their calculation logic. And with a set of tools, it makes it really easy for our developers to create clients quickly and easily. So that's a no-brainer. So with that, with WCF and HPC Server API, what is the kind of end-to-end scenario? What are the steps for a developer to deliver the end solution? So it starts with the developer building using Visual Studio an HPC server. It's a test cluster. And the end result for that is the developer will come up with the client application as well as the service assemblies, the DLLs. Then admin comes in and installs the client application onto the desktop and deploy the service assemblies and DLLs and register the service with the cluster. And now the user is ready to launch the application. And most of these applications, the end user don't even see that cluster exists. They just see that now the performance is a lot faster. And the developers can be an ISV developer. So this step, this step can be a purchase steps, right? We have ISVs use this model, delivering products to the end users. Okay, question about deployment. What are the options? We have 3 options: local deployment, central deployment, and hybrid ones. Okay, I believe best things come with 3. So the local deployment basically means that service assemblies reside on the compute node's local drive. And the performance is good with this approach because it's really close to the actual machine, to where the service host is running. But the problem with this is really hard to update. Think about that you have to update hundreds of machines every time you rev your application. So it's mostly suitable for deploying ISV type of applications because they don't ship as frequently as some of your in-house applications. Now, with central deployment, basically means the service assemblies, there's only a single copy that resides on a file server somewhere. And when the service host starts, it will be loading these assemblies off of the central file server. Advantages: easy to update. Performance is really limited to your file server scalability. So if you have hundreds of nodes hanging off of this file server, you want it to make sure that your file server is running on a beefy box. Hybrid ones means some of the service assemblies on the local drive and others on central drive. Why is it useful? Because you may have some application that uses ISV services and in-house services. So ISV ones can be deployed on the local drive, whereas in-house ones on the central file server. So you get the best of the both worlds. It's easier to update, and you have the performance that's required for your application. All right. Now, without further ado, let's look at how to develop an application. All right. So this one says 164, so slightly faster than 3 minutes. That's the sequential version. All right. So, yes. Oh, thank you. Thank you. There we are. OK. So I'm remoting into a cluster that's in Redmond, Washington. And so what you're seeing here is a Hello World service. It's a WCF service. It defines iService1 as the interface. And it has one operation contract called Say Hello. Just shows you how it's implemented. Really bring that. It's implemented by the class service1. And what it does is it takes its own machine name and stick it at the end of the hello world message so that when the application receives the response, it will know where it originates from. OK, that's just service. Now, let's show you the client. So I'm going to just show you one step. OK. So when I write a client application, this is a console app. And So to actually use the service, I need to add a service reference. This is akin to adding a reference to a DLL. And so adding a service reference actually provides me with a great tool for generating client-side proxies. And I can say discover, and it finds one service in the same solution. So I just want to make sure that's defined the right operation contracts here. It says say hello. It's indeed the one that we want to use. So just going to name hello world service. And click the advanced button. I want to say generate asynchronous operations. And it will become obvious why I need to do that in a minute. Click OK. OK. All right, here I have the hello world service. So what's in it? And it gives me a service one client proxy. And on that proxy, I can actually invoke say hello methods synchronously or invoke that asynchronously. How many of you know .NET asynchronous invocation? Are familiar with that? OK. All right, now I'm ready to code the client. Just show you the code here. It's really 3 steps to coding an HPC SOA client. Only one step has to do with HPC server, and the rest of the 2 steps are all WCF. So the first step is creating a session. So what does creating a session do? After you create a session, what you get is a set of service instances, potentially spreading across multiple boxes, working for you. And you're not going to get millions of service endpoints. You only get one, right? That virtualizes all the service, physical service instances. So to do that, you basically have to identify which cluster you talk to. A cluster is usually identified by a head node name or a scheduler name. And you indicate the service name you want to interact with. And then you just call session.info to create a class of .info. You can actually optionally specify how many, what's the minimum and maximum service instances that you require. By default, it's going to just allocate as many as there are available. Now, and I'm going to go ahead and say create a session. After create session returns, a set of service pool is launched for me, and I have an endpoint reference to actually address to all these service instances as if they are just one. Now, with the endpoint reference, I'm ready to create the service one client proxy. And the service one client proxy is actually generated as part of the service reference adding step, which I just showed you earlier. And in here, basically, I just say providing the session endpoint reference to that constructor, and it will create a proxy connecting to that endpoint. Exactly where that endpoint is, there's going to be an architecture diagram show you that. Then I'm ready to make service calls. So in here, I'm looping through 0 to 99. And I'm going to call begin say hello. So why I do the asynchronous version of the invocation? Why can't I just say hello? Well, you can do that. And it's not going to be very fast. If you say hello, that means this first invocation has to happen before the second invocation. So you're invoking the service in sequential fashion. By doing begin say hello, the call returns immediately without waiting for the results to come to be computed. By passing callback and context that callback function, the actual thread pool is going to be generated on the application side. So whenever the result becomes available, callback will be called per response. So what does that callback look like? The callback, this is all standard .NET asynchronous invocation. It takes iasync results. And from the iasync result, you can actually get the state that's passed, the context that's passed to this callback, which is the client parameter here, the proxy to the service. And then once I got the client, I can say, and say hello. And this call will return the results to me. And then I'm going to say, write the output to the standard output. So what I'm going to do is I'm going to actually build this, no errors. And then I'm going to start debugging. By start debugging, Visual Studio adding actually helped me deploy the thing to the cluster. So if I just show you the view here, Hello World service is deployed for me onto the cluster. And as you can see, that 100 requests coming back, we certainly have no time to count it. It runs. But then, of course, such a simple program always successful, right? So what if, I have a bug in the code, in the services, and it's running somewhere in the cluster? So let me show you one of my favorite features with the platform, which is the debugging capability. So let me hit return to get out of debugging. So what I'm going to do is to go to set a breakpoint in the service, right here. What about the first line? And then I'm going to say start debugging. So yeah, it's repeating the deployment steps. And then what's going to do is going to launch me a set of process view. And so in here, you're seeing that these HPC service hosts are actually in the paused state. And you're actually seeing by just expanding this column here, I'm actually seeing where these instances are running. For example, this one runs on PAC 0607 host. So if I just hover my pointers here, it's actually showing that it's actually PAC 0607. Let me switch one. What about 0601? And it's on host 0601. So you can actually, break all the service and keep switching among these multiple instances and step through them. So for example, I can just step through them. Okay, you just keep breaking in different places, so it's going to get boring after a few seconds. So I'm just going to, delete the breakpoints and say, okay, run to completion. All right, so you got all the responses back. Pretty cool, huh? Actually, I've been showing this capability to a IT manager in one of investment bank. The quote I got back is, wow, I need it yesterday. When we move to the cluster computing, it says the developer experience goes backwards. It becomes really hard to actually debug what's going on in the service. So we hope that with the Visual Studio adding for HPC server SOA, it become really straightforward for developers to and it will inject huge productivity into the developer. Okay, all right, let's switch back to this. So what you're seeing here, and hopefully I can summarize that in 4 bullet points that spells the word easy, is we choose WCF, which is an established platform, and come with it a set of tools. So we don't have to spend time to train our developer. There's a lot of training materials, videos, decks, movies on WCF, right? And as you can see, that as service reference make it really easy as adding reference to a local DLL. And that gives me the ability to quote types and also methods that's available, that's defined in service. Debugging is really streamlined. I don't have to go to a physical box physically, or like logging on TS into the box and find out the process IDs and attach my debugger to that. By the way, before this was available, that was what developer has to go through, a lot of ordeals. Then finally, yes, you don't have to worry about how many instances gets created. And you don't have to worry about talking to them individually. It's the system. The plumbing is done it for you as a developer. So what happens underneath the hood? For a lot of people, when we buy a car, we like to open the hood and see what exactly is under that, right? this is what's running underneath the hood. And what you've been seeing is the actual client application, right? And running off of that is the following support cast. The head node. When you create a session, you have to identify the head node. Here it is. And it runs a piece called job scheduler. And on each of the compute node, there is a node manager. And there's a set of broken nodes. I'm going to tell you what broken nodes are in a minute. But so when the client says create a session, what happens is a request is sent to the head node and to the job scheduler. And what the job scheduler does is look at the request, how many service incidents are required, and then look at whether there are enough idle cores or nodes available to satisfy the request. And if there are, then it's going to launch the broker piece on one of the broker nodes and the whole set of service instances. And this service instances, upon startup, will be loading the service DLLs deployed on the nodes. Be it local deployment or central deployment, there is a way for the service instance to find them. And then service instance is going to call back to the broker and say, hey, I'm working for you. At this time, session creation returns. And the client, upon getting the session endpoint, will establish a create a proxy client, and then start firing asynchronous requests. And as broker receive these requests, it will load balance them upon these service instances. So at this point, some of you may have a question. In fact, almost every time I present this, I get a question from Microsoft internal audience, as well as the external ones, is why do we reinvent the wheel? How come, why couldn't I put an NLB, the network load balancer here, right? Yes, it works. But why not? Okay, let me tell you a story. When I was doing my, when I was doing my PhD, it was late 80s. At that time, my university, my department, the computer science department, doesn't have enough budget to buy every single PhD student a workstation. It was a Sun workstation at that time. So for me as a new student, I have one of those VT100 terminals. How many of you have used that? A lot of you, right? So I have to log on to those workstations. As a HPC student, I sometimes run a compute-intensive job on those workstations. So sometimes I do get some really pissed off PhD student and knocking on my cubicle says, Ming, you're killing me. What exactly are you running on that? It's using 100% CPU. I can't write my PhD thesis. So I got it booted off. And poor me, I often have to come really late at night. So I burned a lot of midnight oils doing my PhD. So the point is, NLB is good for the type of web requests. The bottleneck is really on the backend databases for transactional processing, right? Each request will not consume 100% CPUs, where in this case it's not. So there's no point overcommitting a node with millions of requests. You're just going to slow everyone down, right? So that is why, that's one of the things the broker does. Notice the queue here. It actually throttles back the requests. Even if the client sends millions of requests down its pipe, it's only going to, by default, forward as many requests to a node as there are cores, right? So that's the first reason. Second reason is that not all clients are equal. Some of them are higher priority. There are first class. There are second class. So the more important jobs comes in, what can happen is these compute nodes can be used up. And then the only way to make room for the high priority jobs is that the job scheduler goes ahead and terminate some of the service instances and make them available for the high priority jobs. And I don't think NLB will do anything close to that. So with those two reasons, not overcommitting compute nodes, and the ability to sort of satisfy urgent requests, make us, justifies the broker here. And of course, let's answer the final question first is, In the future, if I develop DLLs, using Azure, do I have to use a different API? Well, the answer is no. It's going to be future-proof. We're going to have service instance in the cloud. So you're going to use the same API developed against the HPC server, and HPC server will be transparently forwarding requests to the new cloud instances. So you'll be able to have your dedicated capacity and also occasionally spillover capability should your workload peak. I'm not just saying this by waving my hands. One of my interns actually done a demo that shows you that you use exact WCF Visual Studio to build the service instances and deploy to the cloud. Of course, using different deployment mechanism, and the thing runs. All right. So now we're ready to actually show you how to actually make that 3-minute thing down to 7 seconds. Let's shift. Okay. So first of all, just show you that what's encapsulated in the service. So the service actually is the price agent option. So 1 million times 20 calculations is the granularity of each request. Now, let's show you what the client does. And first of all, when is the session created? It's actually created when the workbook is launched, when the Excel workbook is launched. And so with the Excel project, there's this hook called this workbook_startup. And when it runs, what I do here is basically call get session. And get session method, which is here, is going to invoke session creation. So it's going to say, I need 12 to 48 instances of agent option services. All right. So now, going back to sheet 1. So with Visual Studio, tools for Visual Studio Office, I'm actually able to insert buttons here. So if I just click the button, this is the logic I defined for the button pushing event. So coming in here, as you can see, that it will start. If it's running on cluster equals to yes, it's one of the cells I capture. And it's going to call begin price option asynchronously. Now, the callback is slightly different. The callback, so let me show you the actual argument. The third argument is the actual cell name. So this will be D2 all the way to M11. And the callback is written in using a lambda expression. How many of you use lambda expression? So basically, I take the IAsync results, and I have to lock it because this is going to be done on multiple threads. I call AND agent option to grab the results, and then I populate the range, specified range with the price, and the actual range is captured inside this result.async state. Then I'm going to go ahead and calculate the min max, average, and standard deviation. All right? So let's go ahead and run this. Oops. No, not debugging. So starting a session. OK, session is starting, is done. I'm going to change this to 1 million path. And I'm going to run it on the cluster. All right. Go ahead. As you can see that, multiple values popping up in different order, right? That's the beauty of this loosely coupled thing. And it's finishing 3.6 seconds. Wow, this time I got more cores, so it's faster, right? That just shows you by adding more cores to this thing, and you can actually get in more speed up, right? OK, now coming back to the presentation. So you say, OK, what I've seen is you've always used like C# to write services, but a lot of my in-house legacy code are written in C++. You can do that too. So the way to do that is actually build a WCF wrapper service for your native DLLs. You can either use C#, use P invoke, or use, better yet, managed C++. And in terms of protocols, we support NetTCP. That is the default binding, and that is the highest performing one. And if you have Java client, or wanting to use some of the C++ client or .NET client, and you can use HTTP, which runs on top of WSI interoperable protocol. Or you can use a custom binding. So basically what this picture tells you, you can use C++ as a service, and you can write Java clients hitting against the .NET or C++ services. Now let's shift here on performances. Well, I thought it would be best to actually encapsulate. This is a contrived discussion, but similar discussion happened before between the customer and the Microsoft solution specialist. Basically, customer just say, hey, how come my application doesn't perform? All my machines utilization is less than 80%. Well, the solution specialist says, okay, what's the message size per service call? What's the measured throughput? 16K, and it's about 700 messages per second. All right. So what's the service call duration? It's about 2 seconds per call. Okay. And how many calls are you requesting? 2,000. Lots of course. Okay, let me do the math. And wow, you've exceeded your sustainable service instances. And customer reply, what the hell is SSI? Okay, background information. This performance chart shows you, and this is done about a year ago and using an 8-core box. So what it shows you is the latency, round-trip latency as a function of the message sizes. And so 3 curves are being shown here. Well, the top one is the gigabit Ethernet, and then there's IP over IB and WSD. So with IB, you get well, slightly better performance in terms of latency numbers. So the lower is better. Now, round trip basically is defined by from the point the client sends the request to the point that clients receive the responses. That's a round trip, right? And this is measured by sending lots and lots of requests in an asynchronous fashion and receive them and time them. So as you can see that, if the message size is lower than 8K, we pretty much deliver, it's actually not we, WCF team delivers you guys with sub-millisecond latency. So it's pretty good, right? But when the message grows up, there's a hockey stick effect. And that's not really good. And the hockey stick effect is caused not by the lack of network bandwidth, no, but by the serialization cost in WCF stack. So the CPU time is the bottleneck there. All right, so let's look at the service, how you profile your service. So what I'm showing here is the time and the number of calls. These stripes basically shows you when the first service stop processing a request and when it stop processing a request. And of course, for simplicity purposes, I assume like all the runtimes, it's the same. So you have all the call duration of all the calls are the same. So that just shows you that for this particular edge, it's the end service stop process first, second, so on and so forth. And as you can see, there's it's almost look like the red and all these colors looks like a parallelograms. And the reason there is a slope is that the slope represents the throughput, number of messages per second, right? If it's really vertical, it means our system has no overhead, so infinitely scalable. But there's always an engineering overhead. And that slope is actually determined by the client machine capability and the broker machine capability combined. If you have a really slow machine, it cannot even drive, it cannot keep the broker busy, right? So those two capability, and also the size of message. So given the same client and same broker box, the bigger the message is, the less steep the slopes are, right? And the smaller the message, and then the more steep, because the broker will spend less time sending the messages or serialize the messages. So with that in mind, how do we determine the sustainable, the SSIs, how do I determine, with a measured slope, measured throughput, what is the maximum number of instances that, my application can scale to? It's actually fairly straightforward. It's like, high school math. Basically, here's your slope, right? Here's the call duration. If you just draw a vertical line from here, and until the slope, these two lines meet, this is the maximum sustainable service instances. So it's actually throughput times call duration. For example, if call duration is 1 second, and therefore your throughput, how many calls you can actually fill up, right? That means within 1 second, if your throughput is 700, and then you can only fill up 700 calls per second, right? Clear? Now, the real curves, right? If your number of service instances is actually below the S here, and you have really nice utilization curves here, what I'm showing you is there's 2,000 cores. So you don't see distinct lines, horizontal lines anymore. It's all packed up, 2,000 lines together. And it's pretty nicely packed. So utilization of these boxes are really high. But if you have, this is greater than, the service instances, what you get is really, really messy, right? What you're seeing here is there's a lot of empty white spaces in the core and time, space. And that's why you have no utilization. So let's map that to the customer problem. Well, the measured throughput for 16K messaging on customer machine is 700 messages per second. And the duration is 2 seconds. And therefore, the sustained service instance is how many? 700 times 2, 1,400. And the session requires how many cores? 2,000 cores. And therefore, the session will effectively only use 70% of the allocated cores. And no wonder it says it's running under 80% utilization. And certainly, buying a beefy box, easiest problem, easy solution is always spend money, right? Throw hardware at the problem. But if it's not the solution, if it's not an option, are there any other options? Well, first of all, let me say that, WCF making serialization of objects really easy. So the inclination of the developer is to just pass these objects down the throat, right? Because the WCF does it for me. But if the actual broker capability does not allow that, and if the speed up goal requires that you throw more cores on it, and here's the option. First of all, increase the call granularity. Make sure that duration is longer. For example, instead of making it 2 seconds, make it 4 seconds, 8 seconds. But sometimes that is not easy because that requires you, adding a set of, some wrappers. So within one request, you may chunk up 10 real requests, and sort of painful to do for developer. So the second, reduce message size is a lot of time a more viable solution. Basically, what I do here is instead of passing the whole data, I'm just passing the pointers to data. So the data might reside in the database or file somewhere, but by passing the pointer, that's call by reference, right? As opposed to call by data. Then I'll let the service load the data for me. Well, the service has a much bigger pipe, gigabit Ethernet or 10 gig E, and so it will be a lot faster for the server to load the data. Second thing, a lot of these applications actually have common shared data across requests. So instead of sending these requests, keep sending these common shared data, you can just stick that into a data cache server or a file share somewhere to store and forward large data. So clients stick the data, common data somewhere, service just load it once and use many times. Velocity is one of the products that's going to be available in .NET 4.0, actually provides a distributed data cache server solution. Now, let me give you an example architecture. So that's used in finance. Basically, the application can be web-based also a fat client, which is Excel-based, for example. And then submitting through the web is a model goes in here, and the business logic layer basically splits up into multiple calculation requests. Or through one of the grid or HPC server API, you get this request into the scheduler or brokers. And then the request gets load balanced across the server where the services are deployed. And then between the actual historical data, real-time market data, the database, there's a data cache layer that stores the most commonly used and frequently used reference data, as well as intermediate results. So in doing so, the database, first of all, is actually freed from hundreds of servers hitting it at the same time. And the server is actually having a really good performance. I/O won't be as of a bottleneck as if you are hitting this database directly. OK. Finally, what's new in HPC? What I've just talked about is the features in the released product. Now, we're going to release a new version of the product next year sometime. And it's in beta 1 now, so you can hit the Connect websites. In this, we have a new find and recollect programming model. So what I'm showing you here is basically the application has to stay there, sending requests and waiting for the response to come. But in a lot of HPC scenario where it's sort of exit the application and come back again and retrieve the results. So we have that programming model in the R2 release. And we also support finalization hooks, so the service upon termination can actually free up the resources that it acquired while it's running. Automatic restart and fail of a broken node as one of the killer features in this R2. That basically ensures that the broker will always stay alive, even in case of machine or hardware or network failure. Then finally, with improved management, monitoring, and diagnosis and debugging. We really believe a sort of end-to-end great management experience and develop productivity. So in terms of fire and recollect is interactive connected sessions. That's what I just said. Now the clients can file the requests, exit, and start up and get the responses. In closing, we pick at WCF as the framework and the tool support. And we use our deployment tools to actually help you deploy the services with 3 modes to choose from. And asynchronous invocation really help you sort of create a transparency. Finally, debugging service through the HPC server add-on really gives a streamlined debugging experience. Remote invocation, we give you a sort of SSI model to help you model your performance goals, measure that. Write granularity, reduce message sizes is going to help you a long way in terms of improve the performance. Finally, we're going to reserve your investment when you move to cloud. Here's a list of parallel sessions. And so I'm just going to stop here and see if there's any questions. Yes?
How does HPC relate to the use of Hyper-V?
The question is, how does HPC relate to the use of Hyper-V? You can actually deploy HPC server itself inside the Hyper-V boxes. But for really compute-intensive type of applications, you do not want to have more than 1 virtual server instances per core, because, as I indicated, that it uses up the CPU. It is very CPU-intensive. And if the service is I/O-intensive, you're going to hit some overhead as well. Does that answer your question? OK. Question at the back.
You start up a session from a client and request 8 cores. Does that reserve those 8 cores for that client for the duration of that session? So that those can't be used by that client?
So the question was, if I request 8 cores when starting a session, do those 8 cores get reserved for that session? The answer is yes. But if the client are not using those 8 cores for an extended period of time, the broker will gradually sort of release those cores for other needy sessions. But when new requests coming back, it's going to try to grow that pool again. Question here.
So is Windows Azure the computation node part by HPC?
Okay, the question was, is Windows Azure the compute node part of HPC? No, Windows Azure actually supports more broader set of scenarios. But if you wanted to support HPC scenario in Windows Azure, you would deploy the HPC server image inside the Windows Azure Fabric.
I mean, for the Windows Azure, they have the support for the computation, the service. I'm wondering what's under the hood for the Windows Azure. Is it powered by the PC or they are different?
Oh, the question is, what is underneath the Windows Azure's Fabric? That's Windows Azure's Fabric. It's not our code. It's not HPC server code. Okay. Any other questions? Question over there. Yeah. Question was, does your HPC server support a version of MPI? The answer is yes. We support, sorry?
I mean, does it require?
Does it? For these type of problem, it does not require MPI. It is for those traditional type of HPC application, the one that is in the quadrant of tightly coupled and loop parallel type of problem, that requires MPI. Question here.
Do you have any recommendation how to get started building up a kind of test environment? HPC?
The question was, how do I have recommendations on how to build up a testing environment? Hit HPC, let me get to the site's resources. There is Microsoft.com/HPC. Hit that site. It has sort of evaluation guides, documents, and sort of deployment guidelines on how you may be able to start evaluating this technology. Other questions? All right. We really want to improve, and is that the feedback? Yes. So please fill out the impact. Really wanted to find how I can improve in the future. Thank you very much for your interest. Okay.